So we've been talking about circuits with resistors. Let me just mention circuits with something other than resistors. We've talked about capacitors too, and everything we've been talking about for resistors really holds for capacitors. The same kind of circuit analysis, right? Kirchhoff's rules still hold. It's just that for capacitors, we know that capacitance is Q over delta V, so therefore the potential difference across a capacitor is equal to Q over C. So that's the potential difference across a capacitor when you're in a circuit. So you could have, we've done this circuit before, so I'm not going to redo it. For instance, there, so you have delta V. Kirchhoff's loop rule analysis gives us that. And we have analyzed this circuit before in lab when we did the RC circuit. Okay, anyway. But let me also talk about what happens if we have something other than a resistor, like, say, a light bulb. There are also inductors, and we're not going to do inductors in this class. I'm just going to mention that. An inductor is a coil of wire. We are going to talk about coils of wire as it pertains to magnetic fields, and we already have, I believe, a little bit, but we will not talk about those in class as circuit elements. RC circuits. What about light bulbs? We often, in place of a resistor, and we've even done this in lab, in place of a resistor, we'll use a light bulb. So instead, we might just have a light bulb. Let's see. That is a terrible drawing of a light bulb, but sometimes we use light bulbs instead. And light bulbs act like resistors. We found in lab that they're not exactly ohmic because their temperature changes so much, so that their their potential difference versus current curves are not flat, so they're not really ohmic, but they still act like resistors, and we can treat them like resistors. And when we're thinking about circuits, we can deal with them in the same way as the resistors. But I do want to let me talk about that, treating them like resistors, but also what the difference is. So let's just think about resistors and take these two purple circuits. Which one of these purple circuits has a greater current flowing? Which one has a greater current flowing? If all the R's are the same and the delta V's are the same, the batteries are the same, which one has a greater current flowing? We'll just call that I1, and we'll call that I2, and ask which one's bigger. Well, you should be able to look at these circuits and say, because the net resistance, the total resistance on the circuit on the left is bigger, that means the current is smaller. So we're going to say I1 is smaller than I2. So then we can replace R with light bulbs and say, okay, let's put two light bulbs in the circuit on the left and one light bulb in the circuit on the right. Ask which one has a smaller current. Well, the one on the left is still going to have a smaller current because a light bulb has a given resistance, and that resistance, the net resistance of the left circuit, is going to be bigger than the resistance of the right circuit. So let me ask then, which of these circuits uses more power? Right? Which one uses, therefore also produces, more power? We have I1 and I2. And remember that the circuit used by or produced by, the power produced by a power supply, the power is I delta V. And so on the left, P1. So we can see that because P is I delta V, then P1 on the left, which is just I1 delta V, is less than P2 on the right, which is I2 delta V, because I1 is less than I2. So the circuit on the right uses higher power, or produces higher power. The power supply produces higher power, and the resistor uses more power. Now you might say, but wait, there are two resistors on the left. But the total power used by these two resistors must be the total power produced by the power supply. The total power used by this resistor must be the total power produced by this power supply. So on the right, we've got more power produced by the power supply, more power used by the resistor. Now we could go ahead and prove that, because remember, the power used by a resistor, the power of a given resistor, is going to be the current through the resistor squared times the resistance. Remember that one? That's just another version of power. So on the right, on the left, So on the left, the power used by the resistors. Okay, so this was the power produced by the power supply. This was the power produced by the power supply. Now I'm talking about the power used by the resistors, which should be the same as the power produced by the power supply. So the power used by the resistors is resistor 1 is I1 squared R, resistor 2, I1 squared R. They've got the same current. And so the total power used by the resistors is equal to 2 I1 squared R. Whereas the total power used by the resistor on the right is I2 squared R. And I2, we didn't actually figure it out, but is equal to 2 times I1. You should be able to figure that out by basic circuit analysis. And so the fact that I2 is 2 times I1, and the power goes as I squared R, means that P1 is less than P2, right? So if we go ahead and plug in this here, we're going to get P2 is equal to 2 I1 squared R, which is equal to, I know I've got to write this somewhere else, P2 is therefore equal to 4 I1 squared R, as opposed to P1, which is 2 I1 squared R. So the circuit on the right produces more power and uses more power. Okay, so the power produced by our power supply is delta V. The power used by a resistor is I squared R, and the power produced by a power supply should equal the power that is used by all of the elements in the circuit. So that's what we just went over. And so what I have shown is that in the particular case shown at the top here is that the circuit on the right produces more power than the circuit on the left. This is relevant in particular to light bulbs, because if these resistors were light bulbs, the brightness of a light bulb is proportional to the power used by the bulb. It's not proportional to the resistance. Well, it is. Oh, gosh. It's proportional to the power used by the light bulb. And the power used by the light bulb, right, the power used by any resistor, is I squared R. So the brightness is proportional to the power, which is also proportional to I squared. So the bigger the current, the brighter the bulb, but it goes as I squared, not as I, right? So, okay, I just wrote it down. The bigger the current to a bulb, the brighter the bulb, and that brightness goes as I squared. And I write in parentheses, it doesn't go as I, because we often think of, if we put more current into a bulb, it's brighter. So you just think of that as linear. It's not linear. It doesn't matter for any qualitative circuit analysis. It actually probably doesn't matter much that it's I or I squared, because just the bigger the current, the brighter the bulb. But it does go as I squared. So let's say I have two light bulbs. They're identical, and each has a resistance of 100 ohms. Now that's not actually going to be true, right? Because the resistance is going to vary with the potential, but let's just assume that it's a constant resistance. We're just taking an ideal situation and saying that the resistance of the bulb doesn't change. And just ask, is the bulb in the second circuit twice as bright as the bulb in the first circuit, or what's the relative brightness of the bulbs? What is the relative brightness? So what we have to do, right, the brightness of a bulb is proportional to its power. Power is like brightness. So we need to know the power I squared R through each bulb. So that means we need to know the current through each bulb. So we can figure out the current in the circuit on the left. We'll call that I1, and the current in the circuit on the right, and that's I2. So that means that the current on the left is 0.1 amp. The current on the right is 0.2 amps. And so that means the brightness is I squared R. We could have done all this without numbers to figure out a proportionality. But anyway, the brightness is I squared R. So I wrote those down, right? The power, or the brightness, is I squared R. And so when you plug in the numbers, you get that the power of the light bulb on the left with 10 volts is 1 watt, and the power of the light bulb on the right with 20 volts is 4 watts. So while the voltage was doubled, the power was quadrupled, right? Because it's 2 squared. It goes as the current squared. It also goes as the voltage squared, but it goes as the current squared. So even though we've doubled the current, we've quadrupled the power. Okay, that's all for today, or for this one. Okay, I've got a matchstick puzzle for you. If you've seen it before, then, well, you know the answer. Okay, so let's just pretend these are all matchsticks, but I'm using the matchsticks to form an equation. So I have 1, 2, 3, 4, 5, 6, 7 matchsticks, right? There's 7 matchsticks because each line indicates a matchstick. And I throw them down and I write in Roman numerals 7 equals 1. Well, that's not a correct equation, but I can move one matchstick, just one matchstick, and make this equation correct. So you want to just move one matchstick and make this equation correct. I don't think it's an easy one at all, but if you can figure it out, you are smarter than me. One matchstick to make this equation correct. Think about it, and I will give you the answer in 3. You can pause it. 3, 2, 1. Okay, so here's the answer. We're going to take this matchstick here, and we're going to move it up, and I'm going to do this. So we have the V. We're going to move it as part of that. And there we go. So we just move that matchstick up and make the V into a square root sign. So you've got the square root of 1 equals 1. Check. That is the trick. Have a great day.